right, so I'm going to record. So just to review, basically something that doesn't change under a change of coordinates, that's a scalar. Something that transforms like coordinate differentials, that's called a contravariant vector. And something that transforms like derivatives, that's called a covariant vector. And if the covariant vector depends upon space-time, then it's called a covariant vector field. And so an example of this is the derivatives of a scalar field. Well, b prime of x prime is the same as b of x. And then the derivatives, well, the derivatives just form a covariant vector. And so we get this expression here. And then that tells us that the gradient of a scalar is a covariant vector field. Now, tensors are just things that transform, that have more indices than just one, 0 or 1, and instead have well, any number of indices. And the most common tensors have 2, 3, or 4 indices or indexes. If both of the indices are lower, then that's called covariant. They're both upper, like this, they're called contravariant, and they can be mixed, one up and one down. And let's see, I see that I've switched to the to Einstein's summation convention here without saying so. So
okay. I remember it.
Yeah, so it's that there's a sum over repeated indices if one is up and one is down. Anyway, if you have a scalar field, then its derivatives, its partial derivatives form covariant vectors and covariant tensors. And if you take just 2 covariant vectors, that's a second-rank covariant tensor. And you can multiply vectors together and you get higher order tensors. The summation convention has something hidden in it. Namely, the summation convention is just that if you have AI and an A lower I times B upper I, then what you really mean is that you're summing over I, typically from 0 to 3. And what's the thing that's a little bit hidden about that is that this thing is then a scalar. And the way we see that is that A prime K, C prime K summed. Well, we know that this thing is a covariant vector, this is a contravariant vector, and so these are the transformation rules. But then we've got this sum over K, and that just collapses by the chain rule into just the partial of XL with respect to XM. But that's just the Kronecker delta. That's just 0 unless L is equal to M. And if L is equal to M, then it's 1. And so this turns into just AL, CL. And so what we see is that a covariant vector contracted with a contravariant vector gets us something that is a scalar. And I use the word contracted. What is meant, the contracted just means you sum over that repeated index. And that's called a contraction. I'm not quite sure why that's an appropriate use of English, but that's what people say. And in particular, if you doubly contract a rank 2 contravariant tensor with a rank 2 covariant tensor, you also get a scalar for the same reason. And what's going on here, of course, is what we noticed before, namely that this structure here is just the Kronecker delta. And so the sum over K is just the partial of X prime I with respect to X prime L, and that's just either 1 or 0, according to whether I is L or I is not L. It's a mixed second-rank tensor, and the delta prime IL would be like this, and we'd sum over, well, the delta kj makes this, makes j equal to k, so we just have this, and then summing over k, we just get the partial of x prime I with respect to x prime L, and that's the Kronecker delta. So the Kronecker delta is a mixed second-rank tensor that is invariant under changes of coordinates. So that's something that's even nicer than things that transform a particular way. This is something that's absolutely invariant. And if we have something that is a tensor that has only covariant indices, then we can say, if it's invariant under transposition, then we say it's symmetric. And if you have a contravariant tensor that's symmetric under permutations of KLM, then it's said to be symmetric. The metric of space-time is usually taken to be symmetric. And the reason I say that is that I think of the metric of space-time as being mainly what gives us an invariant quantity here when you multiply by dxi and dxk. And since dxi, dxk is symmetric, any anti-symmetric part of this would cancel. Some people generalize general relativity and allow for GIKs that are not symmetric. That doesn't affect this equation, and I don't know, it may have some useful consequences. It's not something I've studied. And in standard general relativity, the metric of spacetime is symmetric. A covariant or contravariant tensor is antisymmetric if it changes sign when you interchange the indices. So FKL of x is minus FLK of x. That's an antisymmetric rank 2 covariant tensor. And one way of thinking of a tensor being antisymmetric is that if you symmetric is that if you contract it with an antisymmetric tensor, you're going to get 0. So there's an antisymmetric symbol called what is it? Somebody's symbol.
I remember deriving
Levi-Civitas symbol, I think.
Yeah.
And it's intrinsically antisymmetric. And so if this thing is 0, then T12 is equal to T21, and that means the tensor is symmetric. Now there's something called the quotient theorem, which is interesting, and there are many ways of stating it. So there's not just one quotient theorem. There's a whole bunch of quotient theorems, and I'll just talk about the simplest one here for the moment. So suppose B has unknown transformation properties. We don't know what it is, but that BA with all tensors A is some kind of tensor. Then what we find is then B must also be a tensor. Now remember, a tensor is something that transforms nicely under general coordinate transformations. That is, it transforms according to those partial derivatives that we saw for contravariant, covariant, and covariant vectors. So the simplest example is if B lower I, A upper I is a scalar for all contravariant vectors AI. Okay, so we have this expression. Then since AI is contravariant, we can say that AI prime, this thing, is actually this linear combination of derivatives times the AJs. And by assumption, that's equal to BJ AJ. So we have this equation here. And now if we subtract this from that, what we get is that B prime I, sub I, this partial of X prime upper I with respect to X upper J minus BJ times AJ is 0, but it has to hold for all contravariant vectors AJ. And that means that we can replace this equation with an equation without any AJ and any summation over J. So now we simply have the statement that, well, this equation holding for all I and J, whereas up here it just held for all I because we were summing over J. But since this holds for arbitrary AJ, we can promote it to this level. Now we just multiply by this derivative and sum over J. Well, if we do that, we see that on the left-hand side, we just get BJ partial XJ with respect to X prime K. And so that statement is, and unfortunately, I've got J and K. I need to interchange J and K, I think. In any event, oh no, this is actually okay. So in other words, this unknown quantity BI transforms as a covariant vector. In other words, what we want to do is we want to multiply this whole equation by this partial derivative, and we get this. This gives us a delta, Kronecker delta, and just leaves us with B prime K. So we've got the equation B prime K is this summed over J of partial X upper J, partial X prime upper K times Bj. And this is just the definition of a covariant vector. So what we've learned is if for all contravariant vectors AI, this thing is a scalar, then BI has to be a covariant vector. And it turns out that the quotient rule can be generalized to arbitrary tensors, and the proof in each case is similar to the one given here. Now, what we've got here is, let's remember in electrodynamics where we touched briefly on Maxwell's equations, and in particular, we saw that the homogeneous equations could look like this. These are Maxwell's two homogeneous equations, the ones that are the same whether you're in matter or in vacuum. And they relate derivatives of the field strength tensor to each other. These are generally covariant tensor equations, and they follow from the Bianchi identity. Maxwell's inhomogeneous equations relate the derivatives of the field strength tensor, that's Fik, to the current density and the square root of the modulus, or the square root of the absolute value of the determinant of the metric tensor. And so this is what Maxwell's equations look like when they're written as generally covariant equations. So in other words, the two inhomogeneous equations look like this, and the two homogeneous equations look like that. And here's what's nice about that. You see, because they're written as tensor equations, if we change coordinates, what happens is the equations just get covered with primes, but look exactly the same. And so the deal is, in other words, that's written here. If we can write a physical law in one coordinate system as a tensor equation, so like GJL of x equals 0, then in any other coordinate system, the corresponding tensor equation, G prime IK of x prime is equal to 0, is valid. So in other words, this thing just turns into that, which is the same thing, just with a lot of primes. And the reason for that is that G prime IK of x prime, since this is a tensor, it's given, and it's contravariant, it's given by this product of partial derivatives on GJL. But GJL was 0. And so this thing is still 0. So the equation, this equals 0 in one coordinate system gives us this equals 0 in any other coordinate system. And that reminds me of something that happened when I was a first or second year graduate student, actually. And Sidney Coleman was lecturing, and he had just derived something, and then he turned around and faced the class and said, and so it all follows from the fact that such and such is represented by an equation, something equals 0. And a friend of mine spoke up and said, but Professor Coleman, every equation can be written as something equals 0. And Coleman realized that was true, and all the other students realized that was true. It was about the only time I've ever seen Sidney Coleman caught with a mistake. Huh?
Zeros. How do you prove 0 is a unique number, right?
Okay, maybe if you type what you're saying, because that microphone you've got is just so muffled. Yeah, he was at Harvard. He was a spectacular physicist, but unfortunately he had a brain disease that showed up. I think it showed up in the late 1990s. And he started teaching at Harvard in the late 60s. So basically he was teaching, he had a spectacular 30-year career at Harvard. After being a graduate student at Caltech, I think Murray Gell-Mann was his thesis advisor. And so he had a spectacular 30-year career at Harvard and then just died. And in fact, I was told by somebody that Murray Gell-Mann died of the same brain disease, but in Murray Gell-Mann's case, Gell-Mann was, I don't know, 80, 85 years of age. He wasn't a relatively young man. I mean, Sidney Coleman, when he died, he might have been in his 50s or 60s. He wasn't in his 70s or 80s, I don't think. Anyhow, to get back to the physics, the point is you can take if you have an equation that's written in terms of tensors, you can always write it in the form some tensor equals 0. And then when you do when you change your coordinates, it turns out that all these G's that are equal to 0 just get multiplied by derivatives. So the thing is still equal to 0. Oh, so you were saying something about Yeah, working in biomedical engineering. Yeah, that's a very good field, by the way. Yeah. The disease that killed, I think, Coleman and Gelman was something called Lewy bodies.
Oh, yeah.
And apparently that's a pretty horrible illness. Anyhow, to get on with this, physical laws also remain the same if expressed in terms of invariant forms. In particular, a theory written in terms of tensors or forms has equations that are true in all coordinate systems if they are true in any coordinate system. And so basically, and only such generally covariant theories have a chance at being right, because we have no way of knowing which is the right coordinate system. And so we have to have a theory that's independent of the coordinate system, because we have no idea what the right coordinate system is. And the CMB analysis has provided an indication that this is that we really need relativity, because planet Earth is moving at 1/10% of the speed of light relative to the cosmic microwave background. So we're not even in the right Lorentz frame. We're not in the rest Lorentz frame of the CMB. And so we've got to have equations that are true for true in all coordinate systems. Now, I adopted in much of this book, I use various notations, and one notation is this common notation for derivatives. So there are three ways of writing the partial derivative of a function with respect to, say, theta. One is d lower theta on f, and that's probably the best way to do it, frankly. Another way is f, and then you have comma theta. For example, f comma phi is the partial of f with respect to phi. And then double derivatives are f comma theta theta, and so forth. The advantage of this is the equations become more compact, but frankly, I think probably if I ever rewrite this book as a third edition, I might get rid of this comma notation and just go with this notation, which is somewhat, it's I think clearer. Anyway, excuse me, the one advantage of using indices, of course, is that you can then write d sub partial sub I to represent that. Partial f sub comma ik means a double partial. It looks like this. As I said, I thought this was really a nifty notation when I wrote the first and second editions of this book, but in retrospect, I think maybe this isn't the smartest notation. I know that the guy who wrote that quite nice book, oh damn, I can't remember. Anyway, he said he wasn't much of a fan of the common notation. Anyway, let's go on to basis vectors and tangent vectors. So a point in space or an event in space-time with coordinates x is a scalar in that the point is the same point in any coordinate system. And so the partial derivatives of the point with respect to the coordinates, that then is a covariant vector, because it this is invariant. This is just the gradient of a scalar, and we saw that a gradient of a scalar was a covariant vector. And we can see explicitly that because E prime sub I of X prime, well, that's by definition, it's partial of X prime, partial of P prime of X prime with respect to X prime I. But P prime of X prime is just P of X. And then the chain rule gives us this expression. And then this gives us back EK. So what we see is that these things are covariant vectors. And I think these are nice basis vectors because, I mean, you can see, you can imagine if you were making furniture, say, then they're tangent vectors to the surface of the wood, you see. And you can also say that these equations immediately mean that the change in the point on the manifold meaning this curved space that we're talking about, is the change in the coordinate differentials times these basis vectors, because of course these basis vectors are just partials of the point with respect to the coordinates. And so these form a basis at every point because they vary with the point. And these are tangent to the curved space or space-time, and so are called tangent vectors. And I'm talking here about real space-times, not ones that are complex or fermionic. I'm not looking at those things. They may be quite interesting, and in fact, thinking one way of thinking about supersymmetry is to say that good. All right. One way of thinking about supersymmetry is that actual physical space has a fermionic component, a fermionic coordinate. But of course, there's no evidence for supersymmetry, and it's a very extravagant theory. It doubles the number of particles. So what's the metric tensor? Well, a Riemann manifold of dimension d, what is it? It's a space that locally looks like d-dimensional Euclidean space, and that is smooth enough for the derivatives that define these tangent vectors that I just talked about to exist. In other words, that these things, it's smooth enough so that these derivatives exist. And the surface of the Earth, for example, looks flat at distances less than a kilometer. So just as the surface of a sphere can be embedded in flat three-dimensional space, so too every Riemann manifold can be embedded without change of shape in a Euclidean space of suitably high dimension. This is a theorem due to Nash. And in particular, every Riemann manifold of dimension 3 or 4 can be isometrically embedded. Isometrically means you don't squish it at all. Isometrically embedded in a Euclidean space of at most 14 or 19 dimensions. This is a more recent result by Günther. The Euclidean dot products of example 117, I'm a little puzzled where example 117 is. Oh, that's chapter 1. Yeah, okay. Euclidean dot products of the tangent vectors define the metric of the manifold. So the metric is just the dot product of EI with EK. And it's then just the sum of these things. And summed over what? Well, summed over the components. You see, I said, you see, if this is if we're embedding this 3 or 4 dimensional Euclidean space in a higher space of n dimensions, just as we normally think of an ordinary sphere like the surface of a balloon. We think of that surface as embedded in three-dimensional Euclidean space, the space we live in. In that example, n would be 3, and we'd be summing over the 3, and the vectors tangent to the surface of the balloon would be three-dimensional vectors, but there'd be only 2 of them, because on the surface of the balloon, there are only 2 perpendicular vectors on the surface of the balloon, but they're three-dimensional vectors for a sphere, an ordinary 2-sphere in 3 space. But in more generally, if what we're talking about is a d-dimensional Riemann manifold that can be embedded in n dimensions, then we have to sum over all n coordinates of the basis vectors, and I and k run over the d dimensions of the manifold in question.
Okay.
And because these tangent vectors are covariant vectors, the metric tensor is a second-rank covariant tensor. And so it transforms this way. And it transforms that way just because each of the basis vectors is a partial derivative of a scalar, something invariant. And the change in any point on this manifold is given by a sum over I. There would be d dimensions of that, and each basis vector gets multiplied by the d basis vectors get multiplied by dxi, but these basis vectors are vectors in the embedding space of n dimensions, so you have an n-dimensional dot product here. So G is n by n, and the coordinates here, x, are n-dimensional. Wait a minute, no, d-dimensional. The coordinates are d-dimensional, but the vectors EI are n-dimensional. So the index alpha goes over n dimensions. Anyway, all right, so let's do a couple of examples. One is the sphere in ordinary Euclidean 3 space. So in polar coordinates, the points on the surface of the sphere are r, sine theta, cosine phi, sine theta, sine phi, cosine theta. The embedding space is ordinary 3 space, Euclidean 3 space. And the tangent space is 2-dimensional. It's a plane at each point on the surface of the sphere, a tangent plane. And the 2 basis vectors are the derivatives of the point with respect to the coordinates, either theta or phi. And when you differentiate p with respect to theta or phi, you get these 2 expressions here. So these are the 2 basis vectors. And when you take the dot products of these 3 vectors, you get the metric tensor of the sphere, and it turns out to be this. And when I say the metric tensor, it's the metric tensor for these coordinates, because the metric tensor, of course, transforms covariantly. If you change coordinates, it changes, but it changes in this nice way, like a covariant tensor. The determinant of the metric is r to the 4th sine squared theta. And since the 2 basis vectors are orthogonal, the squared infinitesimal distance is just this. So if you change theta and phi by a little bit, the distance between the 2 points on the surface of the sphere is given by this sum here. Now, here's something that's a bit surprising. And it's that if we change coordinates from the angle theta to a radius, this is really a weird thing to do, okay? This is just a weird, I guess one has to be a mathematician to think of doing this. But if you change from angle theta to r, and you define r as the radius of the sphere divided by some dimensionless parameter, some scale factor, and assign theta, so then you can replace theta in these coordinates with little r. Well, what you find out is that r squared d theta squared is a squared dr squared over cosine squared of theta. And cosine squared of theta is, of course, 1 minus sine squared. But sine squared is this crazy thing, AR over big R squared. And that's, that we can call that 1 minus KR squared if we let K equal to A over R, big R. And so then the squared distance looks like this. So the reason I'm writing this down like this is that something like this happens in the Robinson-Walker metric. There's a change of variables that's similar to this. So let me just, let's see. Just writing a note to myself. Anyway, the r theta metric of the sphere then looks like this. And this thing actually looks a little bit like the Robinson-Walker metric, especially in this form. Anyway, the sphere is what's called a maximally symmetric space. If you can imagine that, you know, what is more symmetric than the surface of a sphere? It just, you know, without any bumps or pimples. I think maybe we can skip that example. Now, our universe, of course, isn't just a Riemann manifold because it has time. And so, oh, you ask, what is a Robinson-Walker metric? All right, let me jump to that in order to show you what it actually is. If we go to GR here, where is it that I have? All right, let's go to here. Yeah, I think I should rename this as the, oh, I did. Okay, Friedman, Lemaitre, Robinson-Walker cosmologies. The metric here is there's a minus sign, minus c squared here, where the time that multiplies dt squared. But then you see it's something over 1 minus k r squared, and then an r squared d theta squared and r squared sine squared theta d phi squared. So this is this is called the Robinson-Walker metric. It's the metric. It's three metrics actually for k equals -1, +1, or 0. And these Robinson-Walker metrics are what we assume our cosmology is, because we're assuming that it's maximally symmetric. Now, is it really maximally symmetric? Of course, nobody knows, but this is the best guess that people have, that it's maximally spatially symmetric. And then what we do is we attach to this maximally spatially symmetric universe we attach simply a line of space-time, a line of time, and then we say that associated with that line of time is a scale factor, A of t. So that when we change our coordinates, the difference in other words, this incorporates the expanding universe. A of small, at when t is very small, A of t is very, very small. And A of t, when t is, 13 billion years, it's much bigger. But the astronomers unfortunately adopt the convention that A of now, 13.8 billion years, is 1. And so that sort of forces the A at early times to be absolutely microscopic. That probably is not the greatest choice in the world. Anyway, we're talking about the metric tensor here, and did I skip the hyperboloid? Wait a minute, what? Yes, our universe has time, so let me just go through this. So our universe is what's called a semi-Euclidean space-time of dimension d, and we think d is 4. Oh, shall we call? Yeah, it is. We can quit now. I shouldn't run over.
I don't wanna. I think you have a class. Wasn't theoretical physics scheduled for 5:30?
That microphone you've got is so muffled. Look, what I'll do is I'll just end class and we'll start 4 o'clock on Thursday, okay? Is that all right? That's the way it's scheduled. Okay. All right, thanks. And have a nice evening. I'll see you Thursday afternoon. And if I screw up and forget, send me an email. Or call me up. You have my phone number?
Yes, I do.
Okay. So call me up if I forget. All right, so I'm going to stop now.
All right. Goodbye.
Bye.